We can also add vectors. Just like with normal numbers, we can add vectors. So if we had a vector of magnitude 3 and a vector of magnitude 2, if they're in the same direction, we would just have a vector of magnitude 5 in the same direction. This answer is called the resultant vector. It's what we get when we combine two vectors. Remember that there is the commutative property of addition that says we can add 2 plus 3 to get 5. We can also add 3 plus 2 to get 5. I looked it up. I was right. Don't worry about it. All right, graphically, we can add them up in a couple of different ways. Looking at the left, we have vectors A, B, C, and D. And then on the right, we have them combined. Let's figure out how we got there. We can move vectors around as long as you don't change the angle. So if you take a look between the left side and the right side, vector B, for instance, has been moved up and to the right. The angle hasn't been changed, but we could just slide it on up. Same with vector C. It went upwards and to the left. And D went to the left. The vectors, just like when we add numbers, can be in any order. But the path has to start at the origin, whatever the origin is, and the vector starts where the previous vector ends. We call this the tip-to-tail method, where we're taking the tip of one vector and then touching it to the tail of another vector. The resultant is the sum of the four arrows you can see on the right as the white arrow. This is a vector that points directly from the starting point to the ending point. The resultant is the shortcut that goes from start to finish. Another way we can add vectors is using the parallelogram method. To add vectors using a parallelogram, we have a limitation that this only works if there's two vectors. I prefer the tip-to-tail method because it covers you in all instances, but for completion, here's another way. Essentially, you have two vectors, and you have to start the two vectors from the very same spot, and then you're going to draw a parallelogram, drawing a line that's parallel to the first vector and another line that's parallel to the second vector, and they should meet, as you see on the right side. The red dotted line is parallel to vector A, which is in red, and the yellow dotted line is parallel to vector B in yellow. The resultant vector is going to also start from the very same spot, but it's going to go to the opposite corner. So where the two parallel pieces meet. This is useful if you just have two vectors and need to do it quickly, need to see what direction you're going to be quickly. We cannot add vectors in the form of magnitude at direction, but we can add vectors using components. Looking at all of the vectors below, there's all the components. You can read them for yourself. The x component of the resultant is the sum of the x components. So 5, -3, -7, and 0. So this tells me my resultant is going to be 5. Then my y component is going to be 3, 7, 10, 6, and -3. We can see that as the white arrow. So what we have also done for those AP Physics C students is we added, whoa, go back. We added the I hat to the I hat to the I hat and the j hat, and the j hat. So we're just adding all of our I hats and all of our j hats completely separate from each other. And that's what we have to do. We have to keep our components separate from each other until we need to combine them, but we're not there yet. And if you wanted to add these 3 vectors, now you would have to resolve these vectors into their components, which means break them apart into their components. And then you could add them. So using trigonometry, SOHCAHTOA, you should get these answers. I recommend trying this out for yourself. Can you get these exact answers? Little hint, we are in degrees. In math class, you're going to be in radians. In physics class, we use degrees. We use degrees when we're dealing with triangles, which in physics class we love. And we deal with radians when we're using circles, which in math class we love. There's your answer, your resultant vector. Now get the direction